Okay, so the next thing we need to talk about is gas equilibrium. We've already talked about basic equilibrium. Now let's tie in gases to it. I told you guys this was coming. Just as a reminder, equilibrium is when we have the rate of the forward reaction equaling the rate of the reverse reaction. So reactants are reacting and creating products. Products are reacting and creating reactants. And at equilibrium, once it is reached, the concentrations or pressures, depending on how we want to think about it, will be equal, or not equal, sorry, will be constant, my bad. Will be constant at equilibrium. So concentrations look like they are not changing once equilibrium is reached. I'm just going to do NC here for not changing. Not changing once equilibrium has been reached. Remember, the concentration of the reactants will not equal the concentrations of the products. In technicalities, we can use our K value to determine which side is more favored. So remember, if K is greater than 1, and remember K is products over reactants. If K is greater than 1, it means our products are favored, and that means there's more products at equilibrium. If K is less than 1, it means our reactants are favored, and there's more reactants at equilibrium. Okay, and we've worked on Kc already. Now we're going to do Kp. Notice C was for concentration, P is for pressure. Okay, which in reality, notice it's the same exact equation. The only difference is P. Keep in mind Kc and Kp will not be equal to each other in all technicalities, and that's just because of the relationship of pressure to volume and moles. But we're not typically going to go there. It is something we can talk about and calculate, but we're not going to do it. But notice it's the same thing. We have our products, C and D, raised to their coefficients, so L and M here, divided by our reactants, A and B, raised to their coefficients, divided by the reactants raised by their coefficients. So exact same setup. The only difference is what we're calculating, Kc versus Kp. Okay, so let's take what we already know about equilibrium and apply it to a gas law problem, a Kp problem. So dinitrogen tetroxide in its liquid state was used as one of the fuels on the lunar lander for the NASA Apollo missions. In the gas phase, it decomposes to gaseous nitrogen dioxide, so N2O4 turning into two NO2s. Consider an experiment in which gaseous N2O4 was placed in a flask and allowed to reach equilibrium at a temperature where Kp is equal to 0.133. At equilibrium, the pressure of N2O4 was found to be 2.71 atm. Calculate the equilibrium pressure of NO2. Okay, so it's an equilibrium problem. If you remember correctly, when we're doing equilibrium, we always want to use our ICE table. Okay. Remember, our ICE table is ICE, I being initial, C being change, E being equilibrium. So we're not actually told an initial concentration of N2O4, which makes this one a little bit different than some of the other ones we've looked at, but it really doesn't affect anything. So we're just going to kind of leave that blank, or you can put a Y here or something if you want to. I'm not going to use X because we use X in our change. But we are told it's only N2O4, so we know this guy is going to be 0. From there, we have minus X for the N2O4 plus 2X. And again, I know it's plus and minus here because I have 0 of the NO2, so it has to shift to create that NO2. So plus 2X, 2's coming from the coefficient because for every one of these, 2 of these are being formed. And we're kind of left with this idea of Y minus X equals 2.71 because we're told that NO2 at equilibrium is 2.71 atms. And down here we have 2X. Now, what in the world do we do with that? We're trying to find this guy, and let me not use brackets, that is not concentration. We're trying to find 2X. We're trying to actually find what that value is. So how do we do that? Well, we set up our Kp expression. Kp is going to be equal to the pressure of NO2 squared, because we have 2 of them, divided by the pressure of N2O4. Okay, well, Kp we're told is 0.133, and that's going to be equal to 2X squared over the equilibrium value, our pressure of N2O4, which we're told is 2.71. From here, we just have to do our math. So we end up with 0.133 times times 2.71, and we get 0.360, and that's going to be equal to 2x squared, which is 4x squared. Okay, so we're going to take our 0.360, divide it by 4, and we get 0.0901 equals x squared. We take our square root, and we get x to equal 0.300, essentially. Okay, now we can plug that back into x, and what we get is 2 times 0.300 is going to give us 0.600. And of course, that is ATM, since that is our equilibrium pressure of NO2. And of course, double check to make sure it actually makes sense. Our Kp is less than 1, so we would expect the fact that, again, K is products over reactants. So if it's less than 1, we are expecting more reactants than our products. So we kind of look at our numbers. We have 2.7 in our reactants, and we have 0.6 in our products. So yes, that does kind of make sense in terms of our numbers. Okay, moving on. Okay, and as promised, we get back to Le Chatelier's principle. Remember, Le Chatelier's principle is the idea that if we have something that's at equilibrium, a system that's already at equilibrium, and we put a stressor on it, it is going to try to reduce that stress and get back to equilibrium. So remember, we have 3 types of changes that can occur. We can change concentration by adding or taking away reactants or products, and we've already discussed that one. We can now look at pressure because we understand gases. And we'll come back to temperature when we get to thermo a little bit later, when we can actually talk about delta H and understand that a little bit more. So let's talk about concentration. Let's review that. If I have a reaction, A plus B, going to C plus D, remember, by changing, if it's already at equilibrium, we know it's equaling K, or our K value is the ratio of products to reactants is equaling K. If I go in here and increase A, I am no longer technically at K anymore. I am now at Q, and we can do that comparison. But basically the idea is, if I add reactants, it increases my denominator. It has to shift towards products. If I was to take away my reactants, it decreases my denominator. It's going to shift towards my reactants. It's basically making up for what just happened. If I increase reactants, it's going to shift away from reactants. If I take away reactants, it's going to shift to reactants. Same with our product side. If I was to increase a product, it would be increasing our numerator. It's going to shift towards our reactants to get back to K. Same idea if I was to take away a product, this would be too small, our numerator would be too small, it would have to shift that way. So same idea. If I take away a product, it's going to have to create and shift towards that product. If I add a product, it's going to shift away and create our reactants. Now pressure is going to change our K as well, but it changes it a little bit differently. It's not quite so cut and dry, so we are not change our K, excuse me. It is not going to change K, but it's going to change into Q. K only changes when we change temperature, if we remember that correctly. So let's kind of talk a little bit about what's going to go on here. If this was a gaseous problem, what happens when we have pressure changes? First off, there's several things we need to keep in mind. We can either add or remove a gas, which is the same idea of changing concentration and therefore has the same effect of changing concentration. So if I remove a gas on the reactant side, it shifts towards that reactant. If I add a product, it's going to shift away from that product and shift towards reactants. But the other thing I can do is change the volume of the container. So keep in mind, this is only affecting one thing. It's only affecting one species, and the other species are going to try to reestablish equilibrium according to it. Changing the volume of a gaseous reaction is going to change all species, and therefore we have to kind of figure out what's going on to kind of get an idea of what's happening. Okay, so let's look at a reaction. Let's say we have the reaction of H2 plus O2 forming H2O. And we're going to say that reaction's at equilibrium, and we're going to say all of these species are gases. So it's a full gaseous reaction. And of course, we have to do our balancing. If I was to write Kp for this guy, or write my expression for this guy, I would have the pressure of H2O squared, okay, and I would have the pressure of H2 also squared on the bottom, and the pressure of O2 on the bottom as well. So that's our equilibrium expression. So let's talk about it. Let's say I take my volume and I decrease my volume. Well, what is that going to do overall? That's going to decrease the amount of space the molecules are bouncing around in. Therefore, it's actually going to increase our pressures. So let's just say Kp, let's say all of these are 1 for whatever that is. Okay, so 1 squared divided by 1 squared times 1. So let's just say Kp is 1 for this reaction. I'm just making up numbers to kind of help see what's going on. If we're increasing the pressure, let's say we increase the pressure enough that it actually becomes 2. So now I have 2 squared over 2 squared times 2. Okay, and again, just making up numbers. It's going to double the pressure for all species, so I'm just doubling my original pressures for all species. So what does that give us? That gives us 4 divided by 4 times 2. So really it gives us 4 divided by 8. Well, what does that mean? That means we are no longer at 1. Technically, we're now at 0.5, and this is going to be our Q value, which means Q is too small. Our K is greater than Q. We can also see our numeric value here that our reactants are too big. So what's it going to do? It's going to shift towards products. Okay, same idea. Let's say instead of decreasing volume, we increased volume. Well, what is increasing volume going to do? Increasing volume is going to increase the amount of space the gas is able to move around in, therefore pressure is going to decrease. So let's say instead of 1, we change these values to 0.5. We're halving, or we're doubling the volume, therefore halving our pressure. So 0.5 squared over 0.5 squared and 0.5, which basically is going to give us 1 divided by 0.5 once everything's said and done. That gives us a Q of 2. Okay, and you can do that math if you don't believe me. Well, now Q is greater than K, or K is less than 1. Well, why is that the case? Well, because now our numerator is too big, which means our products are too big. It's now going to shift towards our reactants. Okay, but that's only true for this reaction, and it's true because of the relationship with pressure and the fact that all species are changing. So how do we figure this out? Here's the idea behind it. By increasing pressure, the reaction is going to shift to relieve that pressure. So it's going to shift to the side with the least amount of gaseous particles, or the least amount of gaseous substances, we'll call them that, species. Okay? So increasing pressure, it's going to try to relieve that pressure. It's going to relieve that pressure by getting rid of some of the collisions, which means shifting to the side with the least amount of substances. Okay, well, what if I was to decrease pressure? Well, it's going to try to increase the amount of collisions, so therefore it's going to shift to the side with the most amount of gases or substances. Okay, well, what if we had a weird reaction where both sides had equal amounts of moles? Well, it doesn't matter how the reaction is going to shift because pressure is not going to technically change, and you can go through and play with a reaction if you wanted to. So H2 plus I2 going to 2HI. In technicalities, these guys have equal amounts of moles of gases, if these are all gases anyways. Okay, so 2 moles of gas, 2 moles of gas over here. So in reality, a change in volume, changing the pressure overall, it's not going to be able to shift. The reaction's not going to be able to shift to alleviate it, so it doesn't affect anything. Some of the other things we might see is adding an inert gas. Inert gas means it's not part of the reaction, therefore it's not actually reacting in any way, shape, or form. Well, what does this do? This is going to increase the total pressure of the system, but it actually doesn't affect our partial pressure. Remember, these are partial pressures in there. So it has no effect on equilibrium at all, so there will be no shift for that. We've already talked about volume. Let's come down here and look at these guys. What I want you to do is pause the video in just a second. I want you to tell me what happens if we decrease the volume of this reaction, increase the volume of this reaction, and we'll decrease volume again here. So pause it, come up, see what you think.